Now let us get into an example of reading and writing into a peripheral register. So in the last slide we talked about the methods, the first method of doing it. In this demo we will see how the method is implemented. Now I am in one of the programming manuals for STM32, which I had mentioned about previously, and I had recommended a download of 4 manuals. So this is one of them. So the manual is PM0214, and we are in section 4.5, which talks about the SysTick timer. Now we are only going to access the register and see how the peripherals are accessed. So the method of accessing peripherals, control registers, everything is the same. So if you understand this part, you should be able to very easily work on any peripherals and control register for, in fact, any microcontroller that you work on. SysTick timer is it's a 24-bit system timer, and it counts down from the reload value. So we'll talk about the SysTick timer in depth later, but as of now, just know that it comprises of 4 peripheral registers, which we need to fill up for it to work in a particular way. Now, suppose you are posed with this problem, and you need to write some code to access these registers. Like we talked about, this has a memory location starting from E000 E010. So we talked about this memory location. So here you have E000 E010, and then it goes up to 14, 18, and 1C. So there they show it this way, but we mean that if it's an increasing address from here, this is E010, this is 14, 18, and 1C. So this is a privileged, the required level is a privileged level, and whenever we start execution, just assume that we are on the privileged level, and this is our problem statement. So we have to access all of these registers and write into them. We know beforehand that there's an involvement of pointer here, of course, and we have to put in some macros. So even before we put in the macros, let us write it in the conventional way, that is without having a macro, and see how we can access the registers. So let us first try to access the STK-CTRL register, that is the SysTick control register, and the reset value is all 0. So let's do that. So first of all, we know that this is a 32-bit register. So STK control, this is the register actually. So this is how the registers are going to be represented in the data sheets and reference manuals. So this is a 32-bit register, and only bits 0, 1, 2 and bit 16 are used. Rest of the bits are reserved. So we'll not bother about that. We'll let us use only the first 3 bits. So for now, let us only read and write the first 3-bit and maybe the 16-bit. So once you understand this, you should be good to access the other registers in SysTick. But we'll try that out. We'll try that out as well, and we will see the problems in accessing the registers this way, and why they are written in the form of macros, and how our register access becomes much easier that way. That is, it becomes much easier to write the code. It's we don't have to type so much and declare every pointer variable to access the registers, and we have to keep a separate pointer for a different set of registers and so on. We don't have to do all that due to the help that the macros provide. Anyway, let's get started. So it's a 32-bit register. So we have to declare a 32-bit variable. So we are using type defs here. So for a 32-bit unsigned, so these are 32-bit unsigned variables, of course, because the registers will not have a sign bit as such. And so what we need to do is we'll just say uint 32, say unsigned t, okay, and let's say it's a, so we can declare a pointer variable to point to the register. So if we have to declare a pointer variable, not only do we have to do this, we'll have to do a volatile uint 32t, okay, star, and then any variable that you want. So since this variable is stk_ctrl, let us name the same. Let's name it the same. So let's do stk_ctrl. Okay. And then, so this, what we put on the right hand side of the equation is something that you may not have seen previously. Okay. That is, we will directly put the address instead of putting the the address of some variable that you have declared or anything like that. So let's do that. So we'll keep the same typecasting, volatile 32 underscore t star, sorry, star, and then we will put the address location directly here, okay? And then we'll try to compile the code. So the address location here is this E000 E010. We talked about it in the previous slide also. So let's do, and since it's hexadecimal, we have to put a 0x in front, E010. Okay. So now let us see if, and now when you are typecasting it, you have to enclose this in brackets, of course. If you do not typecast this number, then there will be a problem. So you have to typecast this number into a pointer of unsigned int 32t and then assign it to this pointer stk_ctrl. So all of this will be compressed into a macro later. So let's try to compile this code and see if this code compiles. So the code seems to be compiling peacefully. So this means that so far we may not be logically right, but we are not syntactically, we are not wrong. So this is fine. Now let's do one thing. Let us just delete this part and try to directly assign an address and see what happens. So let's do this. Now just do a build again and see what Make has to say. So we have a warning. So it says, warning, initialization of volatile unsigned int 32t star, volatile unsigned int from unsigned makes pointer from integer without a cast. So this is an integer, okay, and this is a pointer. This will work, but it says that you need to cast it. So always cast it. So do not leave it like this. Even though this will work, please cast it all the time. So brackets and then cast it so that you don't get any warnings. And this is a good practice actually. So you immediately see that the catch here is that the difference in the way we are assigning this pointer, we are directly assigning an integer value to the pointer variable. Okay, so this is the difference. This is how we are accessing this memory location in this case, but this is just a pointer. Okay, we cannot, so for us to access the memory location, we can do uint 32 underscore t. So if we have to access that memory location, we need to see what is there in the memory location. So once we put the code in debug, we will actually look into this memory location in debug as well. And so when we make changes to the code and when we write stuff and when we read stuff, it will also it will act as a reference, act as a checkpoint of whether we are doing the right thing. So UI into 32T, and let's say that we are 1 and equal to. So if you have to get the value out of this, what you need to do is you need to, so you are aware of this, just dereference this. So do a star stdkctrl and you should get your value back into this one. Okay. Now when you put the code in debug, okay, what will happen is in value 1 you would get back all zeros. So let us see, let us try to put this code in debug. Say okay. Okay, so we have the code in debug. So we do a PLL initialization here. You need not do it at this stage, but anyway, I just want to keep the PLL initialization function here. Don't worry about it now. When we come to the segment on configuring the clock tree, we will know all about the PLL. So now for stepping over, so let's step over and let's come to the next line. So it's for stepping over, we do F6. So press F6, or you can just step over by clicking here. So when you press F6, it goes to the next line. So now we are in this line. Now let us also monitor the memory location here. So you have to go to the memory tab here below and the plus sign and give the memory location. So the memory location that we are interested in is 0xe000e010. Okay. So we have all zeros here, and if you check the value right now for this variable, it shows that it has a value of 0. But yeah, I mean this variable is not yet been initialized. So what we do is we step again, okay, and step again. So if you watch this variable now, it shows a value of 0. But this doesn't say anything about whether our program was right or not, because since the default value is 0 here, whether it actually is reflecting the value or not is something that we do not know. So let's do one thing. Let's write into this register. Let's write something into this register, and we will just use a very basic method to write into the register. So to write, again, we have to, let's go to the next line, and we know, and let's do this. To star stk underscore ctrl equal to 5. So this is supposed to write the value of 5 into the particular register, because stk_ctrl is pointing to the stk_ctrl is the pointer to this particular address location. Right? So stk_ctrl is pointing to this particular address location. So when we do star stk_ctrl, we are dereferencing that address location and putting a value of 5. Just putting stk_ctrl equal to 5 will make the pointer value equal to 5. So remember that. So it has to be a dereferenced value in which we will be putting 5. So let's do that first, and then also let us extract that register into our value 1 variable. So we do value 1 and then do it equal to, again, star stk_ctrl. So star stk_ctrl. There you go. So what I'm expecting to happen now is that the value 5 is going to get written into this memory location. So I hope you understand till now. So we have assigned a number basically at the address location directly to a pointer, declared that pointer as a volatile pointer because we don't want the compiler to be making any optimizations to this. This has to be read every time when the control comes to this line. Second line is where we dereference that pointer and got the value and saw it to be 0, but we are not convinced whether it is getting updated or not, because since it's 0, we don't know anything. It may or may not have updated. Third, here we actually put a value of 5 into the pointer, dereferenced pointer, and then you put the value of 5. You don't put the value of 5 to the pointer, remember that. And then we will again dereference the pointer and get the value into the variable called value1. So let's put this on debug and see whether our scheme works here or not. So this is gone on debug. Now let's step over. So this one we know, so this pointer is already pointing to this. So if you highlight, if you bring your cursor over here, you will see that it says that stk_ctrl volatile unsigned integer 2t, and it says the value is this for this. So this is the value, but this is a pointer variable. Now we are getting the value of stk_ctrl into value1. However, value1 shows 0, and at this point this register also shows 0. That's fine. Now next line, stk_ctrl, we are trying to dereference stk_ctrl, and we are trying to put the value of 5 into this register. Okay, so let's step over and see what happens. So now, as you can see, this register, this address E000E010 has the value of 5. You see this? So the first byte has the value of 5, 05. Okay. So 5 is 101. So if you come here, this is the register, and we have got 5 here. 5 means 1, 0, and a 1. Okay, so great. So you have written into a peripheral register, a hardware. You have written directly on the hardware of the microcontroller. So you have a 101 here. We will not bother about the configuration as to what this configuration is doing. All we are bothered about right now is to be able to read and write from the register. Now let us see if we are able to read from that location. So for us to read from the location, we will just do a dereference of that pointer variable again and put it back in the value1. So let's single step again and see this value1 has a value of 5 now. So we have been able to write into the register, and we have been able to read from the register. Now, assuming that you don't want to write star and you don't want to dereference this every time, just writing a star stk_ctrl. What if the value variable name is a long one? You might forget to dereference it sometime, and it will corrupt your program. So let's add a macro here, and these macros that I'm adding here is not the final one, but generally macros will be in the header files. I'm just putting it here just as an example, so that just as a demonstration. So let's say hash define stk, anything, you can put in anything, ctrl, and then instead of we are putting star stk_ctrl here, right? Just put star stk_ctrl here. That's it. No semicolons and all that macros. You don't put any semicolon and so on here, because this is a macro. Okay. So Now, instead of stk_ctrl, we are going to put this one now. So this is more meaningful and this is less error prone. However, remember that the stk_ctrl value has to be assigned here. Otherwise, this macro is going to fail. It's not going to work. Okay, this macro does only whenever you write stk_ctrl, it just replaces this string with *stk_ctrl. That's all it does. But this is easier to code in. This is easier to type. So we do that. Okay, we just replace it with stk_ctrl. So now let's put this in debug once again and see what happens. We should get the same results as before. That is, our value should get updated in a similar fashion. Let's see. Let's put 7 here. That is 111, so that our we are more certain about the right value going into the register. So it's not. We'll know that it's not the same value. It's not the same value that is remained from the previous run, probably, if that is the doubt you have. So now volatile. So this one is like assigning the value to the stk_ctrl. Now we'll see what happens here. When we step through, stk_ctrl value 1 is 0. So it doesn't throw an, we still don't know. This value has just been copied over, it's 0. So it's okay. So let's be sure about it now. So stk_ctrl equal to 7. Let's go to the memory view. So memory view, it's all zeros as you can see here. Now let's step 1. We have not saved it because see, this one is still showing you the value of 5. So we must have committed some mistake somewhere. So let's see what mistake we have committed. This value should be updated to 7, because this is equal to 7. So why are we getting 5? We should not be getting 5. So let's run it once again. So until you're absolutely certain, you're absolutely sure about this working, you should not trust me. You should actually trust the debugger here. So first one is value 1 is 0. Now this stk_ctrl, the register value should go to 7 now. So it's all zeros. So let's single step. This is 7. So what happened last time is we didn't save the program. We didn't run the debugger once again. We just put 7 and we continued debugging, and that's the reason that happened. It didn't register this line. So now it will work. So now we'll take this value back into the register. So one more step and we see that the value 7 has come. If you want another variation of this, so value 1, we put 7 into 7 here, and then if we want to add something to that value, okay, that also we can do. We can do some manipulation, say with this variable. So we'll do all that. So we'll play around with the variable also. That is, we will have to do some logical bitwise operations on the registers also, which is very important in our case. So we'll see that as well. So I hope you understand this part. So we have made one level of abstraction here. Rather than typing *stk_ctrl, we have done *stk_ctrl or any variable name dereference here. We have written it this way. Now the point is, how can we make it even more user friendly? Now in this case, if we have to say access the other registers, for example this one stk load, which is at an offset of 0x04, that is 4 bytes above this one, we'll have to again declare another variable. Say, so this one we have to do this, and then E014, and let's rename this variable to be something else, that is stk, say stk load. Okay. So this is stk load. So you see how much work we have to put in now. So let's, if we do stk load here, and so this is your second value. So if it is, for that again we'll have to declare another macro here. So hash define stk load. So hash define star stk underscore load equals to, hash define stk underscore load equals to star stk load. So this is what you have to put now again, and for you to access the other register you have to follow that. So instead of value 1, instead of stk ctrl, you have to put, say you have to put stk load here, and then load value you have to change the names here. You have to change your code accordingly. So imagine that there are 100 or 200 peripheral registers and control registers. How much pain it would be for you to actually declare all of this in the main, or declare all of this in your C code. Anything changes, any mistakes happen, and you are in for a big problem. So generally we don't do this. We will see what we do, but nevertheless, for now, for learning purposes, this is good enough. Now what happens is, see, when you are putting all of these things one by one, so volatile, so say for the third one, so volatile, you do for the third register, that is stk val. Okay, that one is it's a read write value, that's okay. So say for stk val we do again copy, control paste, and this is stk val. I want you to see that a pattern is emerging. Okay? So that is the reason why I'm showing you all this. So this is stk val, and then if you go one step further, it is again control key, and what is the next register? It is say stk calibration, okay. So fourth one is, say, stk calibration. stk calibration is E014181C. Smaller caps, anything goes, but that's now. So do you see? So for all of this again, we have to put our defines. Similarly, stk val is star stk val, stk calib is star stk calib, and so on and so forth. Okay. So this list keeps growing. This one keeps, and we have to, every time we have to write this over and over and over again. Is there a shortcut which we can write so that at least we do not have to write this every time? So that is what you saw in the last slide. So what we'll do is we'll do hash. So we'll just copy paste here, but so this is what we'll copy paste here. So we have a hash define. This you already saw. So what we are doing now is we are creating a macro so that whatever you saw here, that is volatile, unsigned, int 32t star, and a number, correct? So if we write addrw and x, that is the address location here, it is going to not only access that particular address location, but it is also going to dereference that address location. Can you see the star here? So this is actually equal to star stk load. Okay, so here we took multiple steps, right? So we we declared it as star stk load here, or calib, whatever, all the variables here. So first of all, we declared the variable star stk load. This is the declaration of the variable. And then when we are actually accessing the variable again, we have to dereference the variable. So stk_ctrl, so this is the dereferencing that we did here. So we have to dereference the variable and put it in value 1. This is doing all of that in one line. This macro does everything in one line. Okay, so addrwx would mean access the word from that memory location. So instead of using these right now, so volatile, so on and so forth, and all these address locations, let us just try to say access again address location, this one, E000E010, following the macro now. Okay, instead of following this. Okay, so we'll leave it here. So now UI into NT32 value 1, stk_ctrl was dereferencing the value. So following these macros, what do we need to do? If we want a word of data from there, we do addrw, and in brackets we put this value. Okay, and then again when we are putting the value of 7, we put this value here, and again stk_ctrl, we put this value. All right, so let's see, let's put it in debug, let's compile it and see what it does. So we are not using these lines directly. Okay, so let's do one thing. So let's comment out this block. Let's comment out this block so that we are sure that this block is not interfering into our business. Okay, so now what happens now? Let's put this in debug and see. So now we have and this is also not going to be used. We are not using this as of now. Okay, so we are building up the macro slowly so that you finally understand what is really going on here. So now go down here, and the first one, let's see, the first value comes to be value 1, that is 0. So let's go have a memory, view the memory, and let's go down further. addrw is 7. So now can you see this value 7 came here now in a different way. So we are accessing the memory. Actually we are doing this under the hood, but we are doing it through a macro now. So every time it encounters addrw, it actually does this star volatile answer in star and that particular address wherever it encounters this. So previously we did it this way, that is we did it through a pointer variable, and then we were dereferencing the pointer, and then for the pointer variable we created a macro. Here it is, the approach is different, and then when you go further again, we see that the value from that register is come here. Now if we go one step further, now even now putting memory locations into this macro doesn't look very safe, because we might go wrong with such huge numbers that we need to put. So we'll not do that until it is absolutely necessary. So now what we can do is we can start naming these locations like we did previously. Like we named these variables as stk_ctrl, stk_load, value, and calibration. So we'll do that. So #define stk_ctrl load and so on. So instead of doing this, what we'll do is put a hash define here, and we'll say cystic base. Let's go cystic base. So since the base of the register starts from this address, this one, E000 E010, we will paste it here. Okay, so this is your cystic base. So what we'll do now is all these registers that are coming after in that area. So this is the base, and all the registers that are coming in that area, we are going to put them as offsets. So we'll do hash define cystic CTRL. It is not going to be star cystic CTRL anymore. Rather than that, we'll just put a number here. So 0x0. So this is cystic CTRL is at that address. So when you say cystic CTRL, it is at that address. So we say it is at an offset of 0. Okay. Now cystic load is at an offset of 4. So here also it says at an offset of 0, offset of 4, offset of 8, and offset of 12, which is C. So so this is how you lay out the memory of that particular peripheral. So cystic load is again 0x04, then offset. So these are in bytes. So these are all in bytes. So these numbers. So what do you have? You have the STK val now. So hash define STK val is 0x, not 04, but it is 0x8, and likewise the next one is STK calibration. So just STK calib is STK calibration is 0x, that is 12. So now we have created a base, and we have all these values created here. Okay. So now how do we access the registers now? So it becomes easier for us to access, and more and the variables become more meaningful to look at. For example, now say we have to access the cystic CTRL register. So generally what we do is we do this addrw cystic base. So it's cystic base plus cystic CTRL. Okay. So this is more meaningful. Though you had to type much more than previous, but chances of you going wrong is very less, because you are typing it in. These are names that you are writing here. So you exactly know what you are accessing here. Cystic base plus cystic CTRL. This is what you are doing. Okay. So this is generally how it is. These registers are accessed. So let us put this in debug. I'm just keeping these values here. So this is exactly what we are doing, but in a completely different fashion. We are doing it through the macros. So let's see. So we should get the same set of values. Now let us do one thing. Let us make it as 2, so that there will be some variety, and we'll know that it is indeed changing. So compilation goes through fine. step through. When we step through, now this is ADDRW cystic base plus cystic CTRL. So cystic base is this address plus CTRL is at offset 0. So this means we are accessing this memory location. So let's see what we get in value 1. Of course, first one we'll get as 0. So let's also open up the memory view, and this is from byte 0 to byte 3. Okay, so 0010 1, it goes like 0010 111213. It goes on like this, okay? Byte wise in this direction. Now again we single step. So when we single step, as you can see, a value of 2 has come here now. So we are sure now that this scheme of addressing is working for us now, right? So now let's get that into value 1, and we get that into our register. So this is one method of accessing our hardware, that is accessing the registers on a microcontroller. This is method 1, but we will not be following method 1. So this was great to clear your concept, but for ST microcontrollers we will not be following this method. We will follow a method which is based on assigning addresses to structures, basically. Okay, so instead of addressing the memory locations this way, that is through hash defines like this, okay, where we access it through a base address plus an offset, we are going to access the memory in a different way, that is through structures that we define for these memory locations and registers. So it is a more I wouldn't say it is a more elegant way, but it is much easier to write. That is, if you want to actually access, they are like accessing elements through a structure pointer. So you don't even have to type so much. It is going to look like this. When you access the values through a structure, it will be like, probably it is going to be like cystic base and just an arrow, that is a structure pointer, and STKCTRL. That's it. Okay, this expression will become this expression then. So you will have to write much less code in that case, and this becomes, it looks more meaningful also. You don't have to, so here it is like, breaking up, the macro is longer. Here it is much shorter, so you can afford to be a bit more lazy as far as this way of addressing is concerned. And we are going to see how this is done as well. We are going to write a structure which is going to map this particular memory location in the same way as these 4 registers, and we are going to access those structures. Now there is a catch in accessing memory locations through structures. That is, in certain cases, if your structure is not properly aligned to a word boundary, that is 4-byte boundary, the compiler tends to put in padding bits so that the alignment comes through fine. And we will see that with an example. When such things happen, you might not be able to extract your intended data from the memory location, and you might be missing out on certain data because of these padding, this unwanted padding that is happening. And there are some ways to mitigate that. That is like declaring a structure as packed and so on. But declaring a structure as packed again causes the compiler, or causes the code to work harder, because it will probably be accessing memory on a non-word aligned boundary. So it works harder. Probably the access will take a little longer. But yeah, so that's the downside, and we'll see all of that. So I hope you understood method 1, and you understood overall generally how the memory access and memory write works. We'll also get into bitwise operations, logical operations, which are very very important. So it is, you don't directly write a number in there. There are requirements to actually clear bits of certain bits in a particular register, and then write into certain bits in a particular register, shift bits, and so on and so forth. So all of that we'll see, and that also requires some understanding of how we work on logical operators. So that chapter is coming up. So logical, I mean to say bitwise operators. So not logical operators, I mean to say bitwise operators.